What happens if we're given a Kc value, but it's not quite in the form we need? What if we need to reverse the reaction or multiply a reaction by a certain coefficient or a certain factor, add reactions together? How do we manipulate this Kc factor to get to the value we need? Sometimes we're going to give a Kc value or an equilibrium expression, equilibrium constant, for an equation we don't have, but we can manipulate that equation into something we do have. And you can still calculate the Kc value. So effects on Kc: reversing equations, multiplying by a factor, or adding equations. Let's first talk about if the equation is reversed. If it is reversed, you can do this one of two ways, by the way. You can either just memorize the rules, which I do not recommend, or you can understand the process and then be able to derive it any time, which is what I do recommend, because I don't have it memorized. I just look at them quick and I'm able to quickly derive it, and then I'm going to get it right every time instead of mixing up the rules. That said, if the equation is reversed, the new Kc is the reciprocal of the original Kc value. What do I mean by that? Well, if I was to write down the Kc expression for A in equilibrium with 2B, the equilibrium expression here would be the concentration of B squared over A. What if I reverse that reaction, and now I have 2B in equilibrium with A? All I've done is reverse the reaction, which I am allowed to do. I can look at the reaction in the other direction, especially because it's in equilibrium, but the Kc expression does change. Let's call this Kc prime just to keep them separate. Kc prime would be equal to the concentration of A divided by the concentration of B squared. Compare these two values, or these two expressions though, and we realize that Kc prime is just the inverse of Kc. Therefore, Kc prime is equal to 1 over Kc. It's just the reciprocal of the original Kc value. What if we multiply these coefficients by a factor? If we multiply them by a factor, the new Kc value is the original Kc value but raised to a power of that factor. So here, A in equilibrium with 2B. Again, we just wrote this next to it, but let's go ahead and write it again. This would be equal to the concentration of B squared divided by the concentration of A. But what if I divided through this reaction by 2, or that's the equivalency of multiplying by 1/2. If I multiply through this reaction by 1/2, I get 1/2 A in equilibrium with B. Now my Kc expression is equal to B divided by the concentration of A raised to the 1/2. Note, the only difference here is that the Kc expression has been raised to the power of 1/2. So now Kc prime, this one is Kc prime, the second one, is equal to Kc raised to the power of 1/2. And if I add equations together, if I add 2 or more chemical equations, the new Kc is the product of the original Kc values. So for the first one, A in equilibrium with 2B, we know that this Kc expression is B squared over A. That is concentration of B over squared over concentration of A. And we've got C in equilibrium with D. We'll call this Kc2. This is equal to the concentration of D over the concentration of C. Now, I'm going to add these equations together. My reactants add together, my products add together. I have A plus C in equilibrium with 2B plus D. Call this Kc prime. It's equal to B squared times D divided by A times C, which is the same as Kc1 times Kc2. There will be times you need to do these manipulations on your own. Either remember the rules, which I find to be more difficult, or remember how to derive it quickly. But you should be able to do this. Remember a couple examples with you guys, but you will have to be able to apply this to not only this system, but in another module we're going to talk about Kp and Kc and the correlation between Kp and Kc. You should also be able to do these on those equations as well. So maybe you need to manipulate your Kc a little bit and then calculate to Kp or vice versa, but you should be able to practice putting all of these concepts together. So determine the Kc expression for H2 gas plus I2 gas in equilibrium with 2 moles of HI gas. And the Kc is 100 with a decimal place at the end, which means we do have 3 sig figs here. The Kc expression here would be equal to the concentration of HI squared divided by the concentration of H2 times the concentration of I2, and this equals 100. Now, what about the second one? Determine Kc for 2 moles of HI gas in equilibrium with H2 gas and I2 gas. On this one, the reaction's been reversed. I'm going to call this Kc prime. Kc prime is equal to H squared over I squared over HI squared. And when I compare it to above, I realize that it's the reciprocal of that reaction. So it's 1 over Kc, which is 1 over 100, or 0.01000. Don't forget your sig figs. And determine Kc for 1/2 H2 gas plus 1/2 I2 gas in equilibrium with 1 mole of HI gas. And call this Kc double prime. Write out your K expression. Concentration of HI divided by the concentration of H2 to the 1/2 times concentration of I2 to the 1/2. And what I realize here is it's very similar to my original Kc expression, except that I've multiplied through by 1/2. So this is going to be the equivalence of Kc raised to the 1/2, which is 100 raised to the 1/2, same thing as the square root, which gives me 10.0. So again, originally 100, I found 2 other values, and again, in another module we're going to talk about converting between Kp and Kc. You should be able to do that conversion as well as manipulate this and pull it all together. So I recommend practicing that.